Okay, so welcome back to the Oxford Discrete Maths and Probability Seminar. So for our second talk this afternoon, it's a great pleasure to have Dhruv Mubayi, who's going to talk on off-diagonal hypergraph Ramsey numbers. Thanks,
Great.
Dhruv.
Thank you, Alex, and the organizers for the invitation. It's a great pleasure to speak. So I'll talk about Ramsey theory. Some people in the audience are sort of experts, some people are not. So I'll start a little somewhat introductory material, maybe for 5 minutes, and then hopefully everything will be clear. I'm not sure what the usual protocol is, whether you want to just interrupt me or write in the chat. I don't really care either way. I don't know if I'll be able to see the chat because there's a lot going on. Feel free to interrupt me or however you do it. Okay, so there are 2 points. There are two main themes to this talk. You probably get this as the talk goes, and maybe I'll come back to it. But the first is that it's a probability seminar also. It's not a probability talk, but a lot of the ideas involve probabilistic analysis. And in some sense, the main theme of this talk, it's implicit, but I'm making it explicit now, and I'll make it explicit later, is to what extent we need probability to solve problems in Ramsey theory. Let's see if this gets clearer and clearer as the talk goes on. There has to be some probability, but the question is, how much probability do you need? And the recent breakthroughs and developments in the field suggest that if you use less probability, that can get you more. So that's one theme. And the second theme is that one of the things I want to present is basically a conjecture in this field that came up maybe about a year ago. And it builds on work that began essentially in the 1970s and due to Paul Erdős and Heinal. And usually you refine techniques and you kind of improve results over the years. And somehow we're 50 years later, we're sort of back to where we were in 1972. So those are the two themes. And let's see when we get to these. Okay, so notation. Today's talk is basically about hypergraphs. K-uniform hypergraphs are sets of size K of n element set. So you have an n element set, those are the vertices, and your edges are sets of size K. I will use K graph as short form for K uniform. And the main protagonist of the day is the off-diagonal Ramsey number, RHN. So formally, this is the minimum capital N, so that no matter how you red-blue color the K subsets of 1 through capital N, that's often the complete graph on K, on N vertices, K uniform. No matter how you do this, you get something in red or something in blue. And the red thing that you get is this H, whatever the hypergraph H is. And in this talk, there'll be many, many examples. You can make your favorite hypergraph. I'll make a hypergraph that we'll come back to actually throughout this talk. So this is a 3-uniform hypergraph that everyone here probably recognizes. It's called the panel plane. So H could be any hypergraph. Think of it as small and fixed. And the blue thing that you want is a large clique. So you should always be thinking throughout this talk, most of this talk, that H is small and fixed, little n is large, and capital N is really large compared to little n and H. Okay, so that's the Ramsey number. Ramsey's theorem says that such a capital N exists. And the talk is about figuring out what this capital N is for various choices of little h. And the off-diagonal means that the h is fixed and the n is large. So I'll say fixed. And the n, I'll put it in blue just to remind you this is large. And of course, this is larger. Okay. So here are some basic examples that we teach in high school or undergraduate or wherever we teach Ramsey theory. So our K3 is 6. These are graphs. This means you do two things. You give a construction of a graph on 5 vertices, which doesn't have a red K3 or a blue K3, and there it is. And then you give a proof that if you have 6 vertices, then you will be guaranteed to contain these things. I won't go through it. I think most people have seen these proofs. But just to settle on the notation. More interesting is our K44 is 18. Some of us may know how to do this. For the construction, you need to two-color the 17 vertex graph without a red K4 or a blue K4. And that's the coloring. The vertex set is the integers mod 17, and you color a pair red if it's a quadratic residue and blue if it's not. This was a construction from Greenwood and Gleason in the 50s. And then you have to analyze this carefully to show that there's no 4 points having the same color. That proves the lower bound. The upper bound is actually quite interesting. It's something that you can assign as an exercise, but it requires a little trick. It uses the idea on the left, which is the standard recurrence in Ramsey theory, but it doesn't quite work. And then you need some kind of parity argument to finish it off. For those that have done this, it's fun. For those that haven't done it, I recommend you just do it as an exercise. Try and prove R44 is 18, less than or equal to 18 using the recurrence that we usually do, and see that it won't work until you do some little parity trick. So that's graphs. And of course, for hypergraphs, we don't know these things. So the notation here is K43 means all 4 points, all 4 triples on 4 points. That's 13, and that's from a computer. And these are basically the only small diagonal Ramsey numbers we know. And so we are interested in asymptotics and large values of n. Okay, so my brief introductory slide about graphs, just to set the tone. And there's one comment I want to make relative to the talk here as well. So there are off-diagonal and diagonal. Diagonal is when the h that I referred to is sort of the same size as the n. And the most important case is when they are both cliques of size n. And here there's very famous problem, and there was a huge breakthrough a few years ago by Campos, Griffith, Morris, and Sahasrabudhe, where they improved the exponential base from 4 to something slightly smaller. And from below, we have an exponential bound. And the big open problem here is to figure out the exponent, whether it's 4, whether it's 2, or whether it's square root of 2, or whether it's 2, or what it is between square root of 2 and 4. But the point that I want to make here is that these are exponential. So for graphs, diagonal Ramsey numbers are exponential. On the other hand, off-diagonal Ramsey numbers are not exponential, they are polynomial. And this began with the well-known results of Aitai, Komler, Semeredi, and Kim in the 80s and 90s, who proved that the triangle complete Ramsey number has order of magnitude n squared over log n. Put another way, if you have a graph on capital N vertices, which is little n squared over log n, with no triangle, then it has an independent set of size little n, which would be square root of capital N log n. There's been intense study to determine what these constants are in front of the n squared over log n. And I've indicated the state of the art. Shearer proved in the 80s that upper bound is 1 plus little o 1 times n squared over log n. And then there were some long sequence of papers, not a long sequence, 2 papers, both of which are very long, 100-page papers showing a lower bound of about 1/4. And it's a major open problem to decide whether the answer should be a 1 or a quarter. Actually, it's interesting. The gap is a factor of 4 between the constants in R3n. And the gap was, well, root 2. Yeah, it was also a factor of 4 in the exponent for the diagonal Ramsey numbers. But they have nothing to do with each other. Okay, so the point is that this is polynomial. And more generally, if we look at off-diagonal Ramsey for a clique on S vertices, where S is a fixed number, at least 3, it's also polynomial. A simple pigeonhole principle upper bound shows you upper bound of n to the s minus 1. And for a long time, it was not at all clear whether this was the right answer. Random graphs gave a bound of about n to the s plus 1 over 2. But then in 2019, Jacques Verstraete and I had a paper where we sort of put these kinds of problems in a different setting, where we related them to some questions in extremal graph theory, which suggested that the answer to these questions should be n to the s minus 1, which is the upper bound, and not n to the s plus 1 over 2, which is the random construction. And this is my first example of what I said at the beginning. It's about the extent to which randomness plays a part in these Ramsey problems. And there was a huge breakthrough a couple of years ago by Sam Matthias and Jacques Verstraete, where they basically implemented the strategy that we laid out in 2019 to solve the first open case, which is off-diagonal Ramsey number for K4. Random graphs would predict that the answer is n to the 5 halves, but in fact, the answer is n cube. And this was using the framework that we had suggested. This specific case was, I think, conjectured or asked by Erdős, but we actually made a conjecture in 2019 for all S, explicitly based on our framework that we had put in. And so that remains open for larger S. But the bottom line is that for graphs, off-diagonal graph Ramsey numbers are polynomial, and diagonal Ramsey numbers are exponential. And for the purposes of this talk, there's nothing more to say about that. Because the questions that I'm going to be dealing with are going to be questions at a bigger scale, questions about whether something is polynomial or something is exponential or something is in between. And in graph theory, we basically know the answer to that question. So that's why. So let's get to the main topic, which is hypergraphs. And most of the talk, 60%, 80% of it is about 3 uniform hypergraphs. Once again, there are 2 kinds of problems, diagonal and off-diagonal. Here, to put things in perspective, the diagonal case is not well understood as it was in the graph case. And perhaps this is considered the most important open problem in hypergraph Ramsey theory, namely to determine the growth rate of diagonal hypergraph Ramsey numbers. By hypergraph, I mean 3 uniform hypergraphs. And here we can have a upper bound due to Erdős and Rado using some application of the pigeonhole principle of a double exponential in n. But the lower bound that we know is only the probabilistic method. So I'll just say that here. So we kind of, maybe I'll put it in red because my lower bounds are always red. So this is just probabilistic method. And that's unfortunate because it seems that the probabilistic method cannot give anything more than this. And here we are failing to get the correct growth rate if we believe it's double exponential by a long, long amount. In fact, it gives, the probabilistic method gives like 2 to the, I think 1 minus little o 1 n squared over 6. And even improving the 6 is a very different, nobody knows even how to improve the 6 to 5.9. So that's the major open problem. It's a bit unfortunate because we don't know now if it's exponential, double exponential. For a lot of the time, people believed that the answer was double exponential. But in the last 10 years, there's been some weak evidence that perhaps it's not double exponential. But the jury's out. We don't know. The conjecture was that it is double exponential by Erdős. Okay, so this is diagonal. So I wanted to set the groundwork. In graph theory, the diagonal is always exponential. Off-diagonal is polynomial. In hypergraphs, well, we sort of think it's probably double exponential, but we're not 100% sure. But this is all we have to go on. So what about off-diagonal, which is the topic of the day? Well, so it gets interesting very quickly. So even if you look at the smallest case is K4. So just to make sure we know what this is 4 points and four triples. 4 twos, 3 triples. Now, immediately, even for the smallest clique, which is K4, the off-diagonal hypergraph Ramsey number is already exponential. And this is another reason why I sort of went back over here and I said for diagonal, it could be exponential or double exponential. It's probably the case that the diagonal is like way bigger than the off-diagonal. And so if the off-diagonal is already exponential, this is probably double exponential. That would be one way of justifying the conjecture. But I'll say more about this. So, and the construction that does this is very, very fundamental, very basic, very important, because all of the new developments over the last 50 years are based on this kind of simple idea. So I want to go through it in some detail. This was done, it was in the paper, or some version of it was in the paper by Erdős and Heinal in 1972, where these questions were, which was one of the foundational papers on these sorts of questions. Okay, so this is the construction. You take a tournament on capital N vertices, and you randomly orient every pair in one or the other direction. That's the randomness. Okay, so your probability space has size, in this specific instance, 2 to the n choose. There are 2 to the n choose 2 tournaments. But notice that the number of the capital N, the number of 3 uniform hypergraphs is 2 to the n choose 3. So if I was taking triples at random, there would be 2 to the n choose 3 ways to do it. But I'm not. I'm only taking edges at random, or directions at random. That's 2 to the n choose 2. So I'm somehow, yeah, so you have like this big probability space of all the triples, like tilde. This is like 2 to the n choose 3. That's if you did randomness. But here we're sort of focusing just on this small part, which is the trip. I haven't told you anything about triples yet, but the triples are given in the picture. So a triple is red if the 3 points that determine it form a cyclic triangle. Okay, so now I've given you triples, red triples and blue triples, and the point is that the number of hypergraphs I get in this way is only like 2 to the n squared, but the total number of hypergraphs I have is 2 to the n cubed. So I have some amount of randomness, but not a full randomness. And this goes to the question, the point I made before I started speaking about to what extent randomness is fundamental for these questions. Anyway, here's a construction. It's very simple and it's very powerful. Let me give a proof that it works. So not only does this construction not contain a complete 3 graph on 4 points, it even doesn't contain 4 vertices with 3 edges, which is even sparser than the thing that we're trying to forbid. And the proof is very simple. Suppose you have 2 edges, WXY and WYZ, that are red. That means you must have directed triangles among these 3 vertices corresponding to these edges. And I just drew the arrows to show that the triangles are directed. And now you immediately see that you cannot have WXZ being red, because W points out to X and to Z. So you cannot even have 3 red edges out of the 4. So locally, you've managed to kind of forbid small local structures. On the other hand, you don't have a big blue clique. Here's the proof of that. Suppose you have a blue clique of size little n. Remember, capital N is exponential in little n. You just calculate the probability that it's blue, right? The probability that it's blue is that all those triples inside are blue. Now there's dependence amongst those triples, but there's many ways to handle that. The simplest way is to just pick a collection of triples inside our purported blue clique that do not share two vertices. In other words, a linear hypergraph or a Steiner triple system, or as close to a Steiner triple system. So you can extract from all these little n choose 3 triples n squared of them, which are linear. And if this is a blue clique, then all of them are blue. And the chance of being blue is, maybe I got the, what's the chance that this happens? Maybe I should have, this is blue. This is pointing that way, that, maybe it's quarter. So maybe I got this wrong. Maybe I should have written 4. Doesn't matter, it's a constant. The chance of being blue is something, and if all these things are blue, then you have e to the minus constant n squared probability. And so the expected number of these blue cliques is, by a simple union bound, less than 1. So that means with positive probability, there is no blue clique of size logarithmic in capital N, and there's no red K4, which is exactly what you need to prove this bound. Okay, and this was the first construction in this area in some sense, but this is fundamental in the field. Not the specific construction, but the idea behind it. The idea behind it is that we had some randomness on the pairs, and we used that randomness together with some not at all randomness, some deterministic rule on the triples from the randomness on the pair. Okay, and already there's an interesting question. And in fact, that's the main question of this problem is, well, when is it polynomial and when is it exponential? So we've already seen that if you have a clique, it's exponential, even if it's a clique as small as possible. So this is the main question of this talk, about what determines whether the growth is poly or exponential or in between. So let's do some very simple examples to give us a feel for this question. So we analyzed 4 vertices with 3 edges. So what about if you have 4 vertices with just 2 edges as the forbidden red object? Well, in that case, it's easy to see that this is actually n to the 1/2 up to logarithmic factors. Another way to rephrase this question is, what is the independence number of linear hypergraph? Because if you don't contain this red object, that means every 2 triples in your red hypergraph share at most 1 vertex. That means the hypergraph is linear, and the blue clique is like an independent set in that. And old results of Phelps and Rödl show that the, oh, sorry, I guess I got this, this quantity, this wrong. I didn't invert it, so let me just fix that. So this should be 2. So the independence number would be square root. So the Ramsey number would be the square. Right. So if this thing was capital N, then the independence number would be square root of capital N. So the Ramsey number would be square, but it's polynomial. On the other hand, if you have 3 red triples, we already saw that it's exponential in N. In fact, there's a better construction that's much more complicated due to Jacob Fox and Xiaoyu He, which improves the tournament construction I showed you from exponential to 2 to the n log n. And this is very nice because it matches the upper bound of 2 to the n log n proved by Erlich and Heinel in 1970. So we actually know the growth rate of this specific Ramsey. But anyway, there's one major problem, which is the following: for which f is this polynomial, super polynomial, exponential? Is there a way to determine it? So I give you the f, it's fixed, you look at it, and you should answer this question. Is the Ramsey number polynomial? Is it super polynomial? Is it exponential? And we know certain things that, if it has only 2 edges out of 4, it's polynomial. If it has 3 edges on 4 or more, or if it's a clique, it's exponential. Turns out this problem is quite complicated. And we've been trying to get a handle for what the answer to this could possibly be. So I have to now start talking about some more complicated things. So the one crucial point is about iterations, or these fractal-like structures. So we say that a K graph or a 3 graph is iterated k-partite if it's sort of k-partite, but it has more than just k-partite in terms of the edges. So you first partition it into k parts. I've shown an example just for 3. And the edges of your hypergraph go between the parts, just like a usual 3-partite 3 uniform hypergraph. So they all have edges with 1 point in each part. These are these red lines. But the iteration part means that you can recurse this construction inside each part. Okay? So you take you could take a complete 3-partite if you wanted. You could take all edges, and then you could cut this up into 3 parts, and then you could take all these edges as well. And then you could keep doing that, and that would be fine. Okay, so that's the definition. A k-graph is iterated k-partite if it has a vertex partition into k parts. By induction or recursion, each of the induced parts is itself iterated k-partite. And in addition, all the edges have 1 point in each part. So what's not allowed is to have an edge which has 2 points in V1 and 1 point in V. That's not allowed. Okay, have to do with anything? Well, it has to do because of this lovely theorem proved by Erich and Heinel in 1972. They proved that if H is iterated 3-partite, then the Ramsey number is polynomial. And this was a very, very important proof, but it looked like just a special case at the time. Or at least it looked like they proved a special case and there was much more to be done. But as we will see, this is perhaps has more importance than we thought. So I've sketched a proof. Let me sketch a proof. So suppose you have a capital N vertex triple system, and it doesn't contain some iterated 3-partite H, then my goal is to find a polynomial size independent set. Here the red edges are the edges and the blue edges are the non-edges. And so the idea is that you do some kind of induction on the number of edges in H. And so what you do is you first, you have these 3 parts in H and then you recurse. First step is you forget about one of the parts and like shrink it to a single vertex. So just imagine that you're dealing with just one vertex here instead of a big part. And then you call that hypergraph H prime. And then by induction, you either find a polynomial independent set or you find many copies of H prime. This is a standard idea in the area. So you have now many copies of H prime, so many that you can sort of do pigeonhole principle and get many copies on the same V2 and V3. And so you get many copies with the same V2 and V3. So you get like many possible X's, X1s, and many here means polynomial. So you get these many copies of H prime where the X1 is like a polynomial size set. And because it's polynomial and everything that's polynomial stays polynomial, you apply induction to either find a polynomial size independent set inside X1 or else find the thing you were supposed to find inside V1 in there. And so this is how you get a copy of H. Okay, the point is that you do some kind of recursive induction proof. And at the end of it all, you can find polynomial size independent sets in hypergraphs as long as they do not contain some iterated 3-partite H. Okay, so this gets us started. It gives us a whole lot of hypergraphs whose Ramsey number is polynomial. And so you may ask, okay, what kind of things do we have? So here are just some sporadic results of theorems in Ramsey theory about these iterated. So these are examples of iterated 3-partite things. Like in particular, they're not 3-partite. Like T3 is not 3-partite because if you color the vertices 1, 2, 3, you don't have every edge going multicolored, but it is iterated 3-partite. And we proved with Bowman and Piccolelli the Ramsey number of this is n cube over log n. This is similar to Kim's theorem about R3T. It was much more difficult to prove the same bound for this hypergraph where you have one fewer edge. In fact, this was a recent theorem with Mateus, Yakshini, and Verstraete, which was essentially using all the ideas that were needed to prove the bound for R4T. We were needing all those ideas and in order to show this Ramsey number. So anyway, so we have some polynomials, and it's very hard to determine what the power is when it's polynomial. But in any case, here are some examples of iterated three-partite whose hypergraph Ramsey is polynomial. Now, these graphs have have an interesting feature, which is that they have edges that share two vertices. And if you remember the tournament construction, the fact that our red hypergraph had edges that shared two vertices was sort of important for us to show that it doesn't appear in these constructions, because we did something random on the pairs, and it was important that these pairs were like shared by two edges, because that's what we said something about, oh, if you have this red edge, then this pair points in this direction, and then we could say something about a different edge containing the same pair. So a very interesting question, which has been open since roughly the 90s, is what if you have hypergraphs that don't share pairs? Such hypergraphs are called linear, sometimes called simple or linear. Hypergraph is linear if every two edges share at most one vertex. And I just drew some examples of linear hypergraphs. And there was a conjecture going back to the 90s. I started thinking about this in early 2000. I heard it from various people, Gödel and others thinking about it. It was basically believed that if you're linear, you should be polynomial. And if you think about this tournament construction, no idea like that tournament construction would work to forbid a linear hypergraph, because the pairs are different for every edge. So they don't interact with each other. This was the main reason why we thought that linear hypergraph should have a polynomial Ramsey number. Now I showed an example here of a linear hypergraph, a loose triangle, where we actually determined the Ramsey number n to the 3/2. It's not difficult to show that this specific one is polynomial. It is very difficult to show that it is n to the 3/2. In fact, this was in some sense a precursor to the result of Jacques and Matthias that R4T is T cubed. The ideas used in this construction were very similar to the ideas used in the R4T construction as well. So this was a widely believed conjecture that linear hypergraphs have polynomial Ramsey numbers. It's not true. So a year or two ago, Conlon, Fox, Gunby, myself, Suk, and Verstraete proved that this is not true. Namely, that there exists a linear hypergraph on k vertices. K is a large constant whose off-diagonal Ramsey number is super polynomial. So it's 2 to the log n to a power that's bigger than 1. 2 to the log n to the root k, in fact. So this was a huge shock, actually, to us. As I said, this was widely believed because any way we knew how to make constructions in Ramsey theory were some complicated variant of that tournament construction, where you took the pairs and you did something, and then you took the triples based on what you did on the pairs. And any such construction will fail to prove a theorem like this, because the probability that you would have an F would be positive, would be too big. Okay, so what is the F actually? It turns out it's not a very simple F. It's a huge F, which probably has 100 million vertices, but it's fixed. F is a 3-uniform linear hypergraph, which has properties of random hypergraphs. So more specifically in our paper, we looked at a k-vertex hypergraph with edge probability 1 over 200k. So with high probability, this thing would be linear, and it'll have about k-squared triples times a small constant. But also it will have other properties of random hypergraphs, and those were important in our construction. Okay, a construction showed another very interesting phenomena that had not previously been discovered. Namely, instead of looking at the Ramsey number versus a clique, one can look at the Ramsey number versus a complete three-partite graph. So this is the graph where you get n, 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 and you have all triples that go across, n cubed triples. Now, in graph theory, we look at bipartite Ramsey numbers versus clique Ramsey numbers. They sort of behave the same up to small changes in constants. And it was believed to be the case for hypergraphs as well. whenever you had a polynomial growth rate of something versus a clique, it was also polynomial versus a complete three-partite, and vice versa. If you think about the tournament proof that I showed you for the K4 minus, it would work also for KNNN, because I had some Steiner triple system business, and I could do that for a partite version as well. So basically, whenever one was exponential, the other was exponential, and polynomial and polynomial. But this is the first example of a hypergraph where the Ramsey number with the complete three-partite is polynomial. This is very easy to show. It's known using many methods in pseudo-random hypergraphs or just hypergraph Ramsey theory. But if you look at the Ramsey versus a clique, it's not polynomial. So this is a fundamentally new phenomenon that we didn't know existed. But in fact, the fact that Ramsey numbers of linear hypergraphs can be super polynomial shows that it even matters in an essential way whether you put here a clique or whether you put here a KNNN. And we didn't think it mattered for these kinds of Ramsey numbers. Okay, so suddenly life became very complicated because we had this conjecture or question about when is an off-diagonal Ramsey number polynomial. We had this theorem which says iterated three-partite things are polynomial. We thought that a linear should definitely be polynomial, but they're not. One can ask some more questions about linear before I move to the main conjecture. And this is a question that's open. For at least 20 years, I've been thinking about this, just the Fano plane. So the Fano plane, for those who don't know, is the one I drew, at the beginning. It has 7 vertices. There's no special importance of it except that it's your favorite linear hypergraph. It should be polynomial, but we couldn't prove that it's polynomial. Now, I mean, we thought all linear hypergraphs are polynomial, but now we found some which are not polynomial. So now it's like not clear. On the other hand, the Fano plane is a projective plane of order 2 over the finite field of order 2. If you take the affine plane, it is polynomial because, as you can see, I've just drawn it for you. And the way I've drawn it convinces you that it is iterated three-partite, right? I've drawn the 4 parallel classes of lines, and the partition is given by the red sets. So this is iterated three-partite. So Erdős-Heinel implies it's polynomial. Fano plane is not iterated three-part. If it was, then we would know it's polynomial. Right? So here's a question. Does there exist a linear hypergraph whose Ramsey number is actually exponential? I didn't explain much about the previous theorem. I just showed you this very weird looking formula, 2 to the log n to the root k. That's bigger than any polynomial, but it's not exponential. So that's an open problem. But this would have been a ridiculous question to ask prior to a year ago because we believed these were all polynomial. Okay, so I can now get to the main conjecture. So this is the sort of the main thing that you should take out of this talk if you forget everything else. We made a conjecture. Oh, by the way, you see a bunch of theorems with a bunch of authors: Conlon Fox, Gunby, myself, Suk Verstraete. This is Hans Yu from Princeton. Some of us, the reason there are all these authors is that we had some workshop that we were going to at the American Institute of Math for 3 years, where we sat for 1 week every year and solved problems in Ramsey theory. And so if you see papers with this set of authors, then it probably came from those workshops. Okay, and then some people got added on at various points for some of our papers we wrote. Anyway, we make this conjecture. It says that off-diagonal hypergraph Ramsey number is polynomial if and only if the hypergraph is iterated three-partite. In other words, we go all the way back to 1972. And we are saying that whatever Erdős and Heinel proved, in fact, the proof that I showed you of this iterated three-partite free hypergraphs having polynomial size independent sets is the only thing you can do. That's our conjecture. If your hypergraph is not iterated three-partite, I can make a construction. It's kind of bold. It was kind of ridiculous, before, because, for example, we thought that like linear hypergraphs would be polynomial, right? and not all linear hypergraphs are iterated three-partite. So we're still sort of playing with fire in some sense, but we are bold enough to make this conjecture. And if this conjecture is true, then proving it is only about giving lower bound constructions, because there is no upper bound to be proved. Erdish and Heinel proved the upper bound. And in this paper, we gave some evidence. So I will show you some results that give some evidence about this conjecture. So we say that a hypergraph is tightly connected if for every two edges, there's a tight path from one to the other. So in other words, if I have an edge here, E, I'll do it for 3 uniform. And F, I can get from E to F using edges which intersect the previous edges in 2 points. So that means you can get from one to the other where you only remove one vertex and add a new vertex. So that's what tightly connected means. And we have 2 theorems that have some evidence for being it for our conjecture. The first is that if you're tightly connected, then you're not polynomial. Of course, you should not be 3-partite, because if you're 3-partite, then it's easy to see it's polynomial. Even if you're iterated 3-partite, it's polynomial. So if you're tightly connected, you're not polynomial. In fact, we have even an exponential lower bound, 2 to the n to the 2/3. On the other hand, if you're not iterated 3-partite and you have at most 2 tight components, then you're also not polynomial. So if you could prove the second theorem with the weakening that instead of saying with at most 2 tight components, with at most any number of tight components, well, then you would have proved our conjecture. Because you have these tight components, and somehow we can handle the tight. If you have a tight component, we can give a construction for it. And if you have 2 tight components, we can also do something like this. So this is a slight some evidence for our conjecture. Maybe still somewhat weak evidence, but it's the best we could do. So maybe I will try to show it to you. You won't understand it, but at least you'll see the kinds of ideas that go into such construction. So I have maybe 7 minutes. How long do I have, Alex?
15 minutes.
Okay, then I have enough time for this and something else. Great. So I give you a construction. You give me your favorite tightly connected, not 3-partite hypergraph. I won't draw it because it's a bit complicated to draw. I give you a construction on capital N vertices, which doesn't contain this H and has no clique. Okay, so there are some parameters, R and L. Don't worry too much about them. They have some relationship to each other, but the vertex set of my hypergraph will be sequences of length L with entries between 1, 2, and 3. So the vertex set will be this, but not all sequences. There'll be sequences that form what's called an R triference code, which means what you think it should mean, right? That means that if you take any 3 sequences, there are R coordinates where they completely differ. So if I take my X is here and Y is here and Z is here, then somewhere there are R coordinates. They don't have to be looking together, where they're like 1, 2, 3, and 3, 1, 2. They're completely different. Okay, and using the probabilistic method, you can make a large collection of such vectors with these parameters. But again, don't worry too much about the parameters, just worry about the ideas of the. And now I give you the coloring. So the coloring is this. You give me 3 vertices, which are vectors, U, V, W, and I will tell you if it's red or if it's blue. So what do? I first, for every pair of vertices, I look at the coordinates in which they differ. That's what I call C of UV. And because it's an R triference code, there are many coordinates where they differ. In fact, if you take even three vertices, they differ in R coordinates. So 2 vertices definitely differ in R coordinates. So that means that you have at least R coordinates where they differ. And what you do is now you pick one of these coordinates at random. Pick a coordinate at random. That's phi of uv. And now I tell you when an edge is red. A triple UVW is red if this phi that you picked at random for UV, for VW, and for UW was the very same. So that's a very explicit description of this hypergraph. By the way, this is very short, but this took a very, 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 very long time to come up with. There were many, many, many failed attempts for several years by many of us before this idea came. Okay, but I hope it's clear what it is. And let me just show you. Well, maybe I just do a quick example. So here you have 11 coordinates. Here I gave you UVW. I wrote down what C of UV is. So these are like the coordinates in which they differ. So like this is like 5 is in here because they all are different in 5. So I write down all the coordinates that they differ in. I pick a random number in each of these sets, and if those 3 random numbers are the same, I make it red. In this case, I picked 5 for all 3, and so I made it red. Okay, so that's the construction. I'll prove only the easy part. I won't prove the hard part. I'll prove that there's no tight, there's no red copy of H. And all I have to show is that if you have a tight component, you're going to make it 3-partite. I have to show you it's 3-partite. If you have a red copy, it's going to be 3-partite. And the reason is very simple. Suppose you have a red copy. So look at an edge UVW. So why is it red? It's red because all of these pairs have the same coordinate that I chose. So this phi function, which was choosing a coordinate, was the same thing. That's why I made it red. And so what happened in that coordinate? Well, V was 1 and W was 2 and U was 3, or some version of that, right? They had to have 1, 2, and 3. So whatever V was in that coordinate, that's the class that I put V in. And whatever W was, I put that W in that class, and similarly for you. So what I have done then is colored every vertex or assigned every vertex a number between 1 and 3. And that's my X1, X2, X3. And this actually gives me a consistent coloring. So that means that every edge that I have is going to have 1 point in X1, 1 point in X2, 1 point in X3, because it has this, because this phi propagates, because I'm in a tight component, I can move from one edge to another through pairs. And if I move through pairs, this coordinate stays the same. And so I get the same, the consistent partition. So that means if you have a red copy, then it must be 3-partite. And then you have to do some probabilistic method to show that there's no blue clique. And the issue is you don't have independence, but we can take care of that using some inequalities and using probabilistic method. Okay, so there's a high-level idea. And in fact, this is the high-level idea under the Erich-Heinel tournament construction, and basically all constructions for the last 50 years on all off-diagonal hypergraph Ramsey problems, except for the lower bound for linear hypergraph, which I haven't told you about. And the idea is you do some randomness on the pairs, and then you use that randomness for a deterministic rule on the triples. So in this specific case, what we're doing is for every pair like UV, you have a set of vertices. These are the coordinates. So here, up here, you have the coordinates. So for every UV, you can look at the coordinates in which they differ. So you have these sets on the top, and then what you do then you do something random. And the random thing that we did is for every set C of UV, we chose a random number. And then we add an edge, a UVW, if these random numbers are the same. So this is like a high-level picture of a large class of constructions in hypergraph Ramsey theory, which we call pair construction. For the obvious reason, you do something random on the pairs, and then that determines what happens on the. And basically, all constructions use this some version of. So let me say just one curious problem, that we had some things that were polynomial and some things that were exponential. And you may wonder if something can ever be in between. And we found a theorem, Conlon Fox, myself, Suk, and Verstrata, of a strange Ramsey problem where it's in between polynomial and exponential. It's the Ramsey number of K4 versus not a clique, but a star. So a star is what I've described over here. It has n+1 vertices, all the triples that go through one point. If you do extremal set theory, this is the extreme configuration in the Erish-Corrado. So if you look at this Ramsey number, it's between 2 to the log squared n and 2 to the n to the 2/3. And this is the only example where we know of where you have a reasonable hypergraph Ramsey number that's neither polynomial nor exponential, which was quite interesting to us. We don't know any such theorem where we replace this thing with n, or if such a thing even exists. Maybe it always becomes 2 to the n if you're not polynomial. Okay, so that's a nice. I mean, you can rephrase this problem about coloring the edges in a grid red blue, and you either want to find a red square or you want to find a blue clique in the rows or the columns. So I can let you think about why these two problems are sort of the same. This blue clique in the rows corresponds to this part, and this red thing corresponds to this part, where you're coloring not all triples, but only triples between two parts, but they're basically equivalent. So we solved this grid problem, and equivalently, you can solve this Ramsey problem. Okay, so let me say one more thing about polynomial versus exponential. And this is related to an old question of Erdős and Heinel. I will go kind of fast through this part, and just have to excuse me for that. So I need to make one definition, GK of S. GK of S is the maximum number of edges in an S vertex iterated K-partite hypergraph. For graphs, this doesn't make sense in some sense, because once you keep iterating this construction, you can get a clique, right? You already had two cliques, and you take them and you put all the edges between them, you get a clique. So for graphs, it's a clique, but for hypergraphs, you don't get cliques, you get these iterated hypergraph things in the Erdős-Heinel conjecture. Turns out the number of edges you get is some fraction of S choose K, K factorial over K to the K minus K. And the way you achieve it is by taking everything as equal as possible. The point is G sub Ks is a number. For every S and every K means K uniform. This is just the number of edges you can get in an iterated K-part. And recall that if you're iterated K-partite, you have polynomial Ramsey number. And we can define the collection of hypergraphs which have more edges than iterated K-partite ones do. So HSK is going to be all S vertex hypergraphs with more than GKS edges. So they necessarily cannot be iterated K-partite because they have too many edges, more edges. And Erdős-Heinel conjectured in the same 1972 paper that you can forbid all these non-iterated K-partite hypergraphs and have logarithmic independence number. More precisely, that the off-diagonal Ramsey number of this family is exponential. In other words, there's a construction. There's a construction on capital N vertices with the independent set is going to be log n, and there's going to be no copy of this thing. No copy of this thing with lots of edges. That does not exist. He offered 500 for this projection. And 4 years ago, Razbarov and I proved this for all hypergraphs that have uniformity at least 4, which was actually the hard case of this conjecture, thought to be the hard case. K equals to 3 was known for many cases, but it's actually still open for certain cases. So even though we thought K equals 4 and larger was the hard case, it seems K equals to 3 is harder. At least that remains open. And the last part, let me just show you the construction, just to continue this theme of probability and pair constructions in Ramsey theory. So I have to make a construction. I'll do it for K equals to 4. So I'll construct a 4 uniform hypergraph with logarithmic independence number with no S vertices which have the number of edges in the iterated formula. Okay, here's the construction. It's very simple. The hypergraph is on the bottom. But the way you get it is you start with any 4-vertex rainbow tournament. So take your favorite tournament, doesn't matter which one. I just drew one at random. Take 6 different colors, color them with 6 different colors, and put arrows in any way that you want. So I arbitrarily, I just did it in the example. And now I give you my hypergraph. So what do? You take capital N vertices. For every pair, you do 2 random things. You randomly orient a pair like a random tournament, and you randomly color it with one of these 6 colors. So I've got a random graph tournament, colored tournament. And now I just tell you when a hyperedge is red. I hope you can see it. A hyperedge is red if the thing that you've colored and oriented looks exactly like T. Okay? So that's a random hypergraph. That's a hypergraph. And now I have to convince you of 2 things. It has small independence number, and every time you take S vertices, it has few edges. And few is this GKS. And then we would have solved this problem. So, so the blue part is very easy. It's the thing we did with the tournaments. Let me convince you there's no blue clique of logarithmic size. Suppose you have a clique of logarithmic size little n. What's the chance that it's blue? Well, again, we do the same thing with the tournaments. There are these 4-element sets. They intersect each other, but that's okay. Just take a collection of them that don't intersect. Take a Steiner system, the green one. There's about n squared of those, right? So the number of these green edges is about n squared. And now you have independence amongst these. So what's the chance that a given thing is blue? Well, you just calculate it. I mean, you know exactly what has to happen if it's blue. It should not be a copy of T. And you just do a calculation. You see how many ways can you make it so that it doesn't make a copy of T. It's some number less than 1. I think it's this number. And so the chance that this is blue is that all of those green triples are blue, which means you raise this number to the n squared power. And then you just do the union bound. The expected number of independent sets is n choose n times the probability, which is less than 1. Nothing really new. Very simple stuff. The hard part is, of course, the red. Normally the red was easy. Here the red is hard. So there's no red graph because we proved, this is our main theorem, that, and our theorem has nothing to do with probability. It's a deterministic extremal theorem. That if you are given a 6-edge colored tournament on vertex set S with little s vertices, the number of copies of T is at most the number in the iterated 4-partite construction. That's an extremal theorem about the inducibility of colored directed structures. And that shows that the red object is forbidden. And it's tight. Our theorem is tight. There is a construction of a 6-edge colored tournament where the number of copies is exactly G4S, exactly in the way you would suspect, which is you take a construction and you iterate it. And that has that many copies of, if you look at how many copies of this tournament there are, it's exactly the G sub K of S, because you can take one from each part, or you can take everything inside each part and recurse. So, but the theme is that, again, what did we do? We did randomness on the pairs. We had some amount of randomness, but then we did something deterministic. And this is the theme of these off-diagonal hypergraph Ramsey problems. And let me end just with some conjectures. I had something else which I won't talk about, but maybe 3 conjectures that this set of authors made. We've thought about these at length, but we think maybe these are true. So the first is about the growth rates. We talked about polynomial, and then we talked about things that are 2 to the n log n. But the question is there a single 3 graph whose off-diagonal Ramsey number is exponential in n, 2 to the constant n? We can find families for which this is true, but not a single one. So it's an open question, don't know. The second one is very hard. It's about off-diagonal Ramsey numbers for fixed cliques. The conjecture is that you can get larger than any power of n in the exponent. So this is hard. It's related to this $500 diagonal question, because if these numbers keep increasing, if these C's keep increasing, then you suspect that the answer could be double exponential for the clique. Note that even when S is n, the best bound we have is when C is 2, like 2 to the n squared over 6. So this is a difficult thing, but we think it should be true. Current best is 2 to the n log n. And finally, back to the linear hypergraphs. we showed lower bounds that are super polynomial, but we suspect there should be upper bounds that are bounded polynomial, exponential in a bounded polynomial, i.e. linear hypergraphs should not behave like cliques. There should be some much smaller upper bound. So these are just some of many, many questions that we have in this area. But the main question is the conjecture for when a hypergraph has off-diagonal Ramsey number polynomial. That's all I have. Thank you very much for listening.
Thank you. Do we have any questions? So actually, I mean, one thing I wanted to ask was, so you've got these sort of a few cases where random doesn't give you best. I mean, so purely random doesn't give you best, like R4T and
in graphs.
In graphs, yeah. Is it known more generally? I mean, so say in graphs, so what about R5T? Does R4T give you any help at all in knowing whether random is best there?
Oh yeah, this has been well explored. After this theorem of R4T, everybody went into this game for a while, right? The question is whether, so what's the explicit question here? Whether R5T is not
how generally can you say
random.
That how generally can you say that random is not optimal?
Well, unfortunately, we can't say it because we don't have a better construction for R5T than n to the 5 plus 1 over 2, which is n cubed. And that is random. But we also didn't have a better construction for R4T than n to the 5 over 2 until it was shown to be n cubed. So it's possible, although I don't remember, that there's some versions that there can be some extension of this construction that gives another n to the 5 halves. Gives another n cubed for R5T. So maybe we can match random with non-random, but I have zero belief that random is the correct answer for RST for s greater than equal to 4. I mean, we basically know what we have to do to prove n cubed or n to the s minus 1. We have to construct these objects in finite geometry, which we can't construct, but there's no reason they should not exist.
Okay. But at the moment, there's no way of using
R4T to get R5T or something.
The sorts of construction there to build something higher.
No, we've not been able to beat random. When we beat it, we will just beat it. That's how it's going to work, I think. I'm not even sure if we can match it. As I said, I'm not 100%. It could be that random is the best for R5T as of now.
Other questions? Okay, actually, I had one other. So you're bound with Razborov on these sort of multicolored the rainbow tournaments. That didn't depend on the orientation. That was just optimal was just a recursive.
Right. So that's a good question. So your question should be the even better question is like, why did we do these, or why did we do this? Like, why didn't we do anything else? And the answer is that if you put the orientations in, it gets easier to prove. You didn't need the orientations for this for the construction, and you did not need it for this part at all. You just needed some number for this probability. The orientation was to prove this theorem, right? That this extremal theorem. And your question is, do you need the orientation? So this is our theorem. And the answer is no, you don't. In fact, I have a paper which says you can prove the same theorem without the orientations. But then S has to be like 11, not 4. So it gets easier to prove a theorem of this sort if I have orientations than if I don't have.
I see.
But the same theorem should be true without the orientations.
Okay, so your S at least 11 is from the proof rather than what you believe to be true.
Correct. Yeah, it's not going to be true for S equals to 4, perhaps, for without the orientations. But for starting with 5, it should be true.
Good. Do we have any other questions? Okay, so let's I'll pause or stop the recording.